All right, so I will just show a small part of our processing package in for dealing with radar data, and I will show how we identify ground clutter and how we correct it, because I think ground clutter is one of the most of the sources of errors that are the largest. That gives the most annoyance, if you could say so. First, we have our Rainbow software, which is the manufacturer software, which has the signal processing. So that's actually the software that are operating the radars. And in the signal processor, we have Doppler filtering, which is quite standard these days. What does this? It looks at how much movement there is. So, for example, if you're looking at mountains with the radars, you have zero velocity, and it should be flagged as clutter. The way the signal processor does that is they make this frequency, and they remove everything that is close to zero, and they interpolate so that you should remove the clutter. But in all these cases, you are just lowering the clutter, so you have a lot of residual clutter left. And that is what I will deal with. So some strategies to locate the residual ground clutter. You could, of course, manually create those maps and say that this and this pixel is clutter. For example, you can do that with wind farms, because the Doppler filter fails on wind farms since the blades are rotating. And so there, one method is to actually manually say that these coordinates are clutter infected, so they have to be removed. Another method is to make a frequency map, where you just count every pixel in your data that it's over some threshold, and then the higher frequency will indicate clutter. For example, on the image you see here, you have the range on the y-axis and the azimuth gates on the x-axis, and everything above 80% here is typically clutter. You could also use a cloud mask from satellite. That's what the Opera composites are using, but we see that on our latitudes, the coverage for the satellites is not so good. So you are also removing a lot of precipitation with using this cloud mask from a satellite. So we have to use something else. So today we are looking more on how the signal processor handles the Doppler filtering. So we just look at the difference between the unfiltered data and the Doppler filtered. And then you get a data type that is called clutter corrected. That's in dB. So the higher the dB, the more the signal processor has tried to fix that region. So here, everything above around 5 dB is clutter, and we can use that as a mask to get rid of the clutter, like so. On the left here, you just use threshold on this corrected field, and then all the yellow pixel are masked as clutter. We clean up this mask with some image processing techniques, and the image on the right, you can see you have the rain on the right, and all the clutter has more or less been removed. The remaining clutter here is so low in reflectivity, it's not important. So while we are doing that, we also need to fix the clutter that we have removed, because it gives holes in the data. Of course, when you just remove something, you need to replace it with something. And we are using an image processing technique called Inpainting, which does the jobs pretty well. You can see on the two images down here. So the problem is how to fill in the blank pixels. It's not so easy to just interpolate from the surrounding areas, because how do you choose the pixels and so on. You could also extrapolate from higher elevations, but that is also not so easy. But one good method that we think is to use image processing, which is a variational problem. I will not go so much into the details, but the three references here are pretty good that describes the method. The image on the right here has been inpainted, and the important thing here is that the features in the image are actually preserved, like the bright spot here, which has more rain, and you don't have so much where the hole is, so you don't want to inpaint higher points if there is not in the fixed region. So this method will handle it pretty good. And then I will show some examples, and first without rain. You can see the iterations on the animation here. That is the image I showed you earlier, where we are just filling in data that are surrounding these areas, and now we are just inpainting noise into the blank areas. So this is of course not entirely correct, but these values are so low, so it won't affect any end products, because you will threshold the image later anyway. So and you can also see on the 2D Cartesian image that all the reflectivity around Oslo region here, the eastern part of Norway, is only noise. It's only ground clutter. So this is with and without the clutter. And then I will show an example of the data with precipitation. You can see all the bright spots on the left here. That's actually clutter, and all the mid values around 0 to 20, that's precipitation. In the middle image, you have the Doppler filtered that we get from rainbow, and you see there are still a lot of residual clutter. The signal processor has removed some of it, but there are still quite a lot residual clutter. So, and on the right you have the difference, or the clutter corrected values. So if we create a mask for this one, just saying every value over 5 dB is clutter, and we use this mask on the image, you can see we are left with a lot of holes in the image. And here we can use our inpainting algorithm to fill in the holes. And here you can see the iterations that are filling in all the errors, or the missing data after we have cleaned it. So, and the upper right one, you have the residual clutter. On the right lower image, it's just flipping with and without clutter. So every value is 0 above 20 dB, it's clutter. So and here is the last animation showing data with and without precipitation. On the left, you have with precipitation. The upper is corrected and the lower is with clutter. And on the right, you have the same algorithm without precipitation. Yes, so I think that's it.